In Module 18F, I want to go ahead and finish up talking about titration curves, and then also talk a little bit about indicators, specifically color indicators, how they work, and how we can use them, and how we can select an appropriate indicator to help us in a titration. So in the previous modules, we talked a lot about titration curves, but we were looking more specifically at monoprotic acids. Monoprotic meaning they have one proton they could lose. What about if we talk about polyprotic? Polyprotic means like diprotic or triprotic. So for example, for diprotic, we can use the generic form H2A, meaning it has two protons it can lose. Oxalic acid, H2C2O4, is a perfect example of a diprotic acid. Oxalic acid has this general structure. And oxalic acid specifically can lose this and this proton, both of them. It's going to lose them at different points, though. It doesn't lose them at the exact same point. One would be at the first equivalence point, and the second one at the second equivalence point. It's easier to remove the first proton than it is the second one. Which proton? They look both equivalent, right? No, that kind of is true, but they will lose them at different points. We could also have a triprotic acid. We write H3A, means it has three protons it can lose. Perfect example of a triprotic is phosphoric acid. It will lose all three of these protons, but in three successive steps. So each one would be lost at a different point and a different equivalence point. And in triprotic, we would see a third equivalence point near the top of the graph. So you need to be able to recognize, looking at these, is it a monoprotic, diprotic, or triprotic? Again, monoprotic would have one equivalence point, diprotic has two equivalence points, and a triprotic would actually have a third equivalence point. The first equivalence point is when it's going from H2A to HA minus. Second equivalence point is when you have HA minus going to A2 minus. And halfway to the first equivalence point is your first PA value, and halfway between the first and second equivalence points is your second pKa value. Some acids, when you look them up in the book, you'll see that they have Ka1 and Ka2. You will see that here as well, the pKa1, pKa2. So acid-base titrations, a little bit of review from first semester. What's happening in acid-base titration? We can do this either direction, but most often we have an acid that we are titrating with a base, meaning the acid is our analyte. The base is our titrant, and we are adding base. We start adding base to our analyte, and we start neutralizing that acid. Midway through the titration, we're starting to see some neutralization happening, and eventually the neutralized solution is indicated by the endpoint, which is signaled by an indicator changing color. We do read burettes backwards per se. We read the final volume minus the initial volume, because burettes are read from a 0 mil mark, actually 0.00 mils, to 50.00 mil mark. They are graduated to the 0.1 mil, so we estimate to the 0.01 mil. If I have my volume here, I would say my volume is 2.00 mils. Even though it would be this portion that's colored in, I would count that as 2.00 mils. Reading burettes is a very specific technique that you do need to learn. You see this in lab, and you guys should be reading these correctly. But again, it's always volume of the base added is the final minus the initial volume. So what is an indicator, and how do indicators work? Indicators most often are a type of organic dye that will change color depending on the pH of the solution. The color is completely dependent on the concentrations of the indicator in its protonated and non-protonated form. In minus is non-protonated. It's the equivalent of A minus. HIN is the protonated form. It's the equivalent of HA. Weak acids, they establish an equilibrium in aqueous solution. So these organic dyes are weak acids. Our protonated form reacts with water to give me the non-protonated form, NH3O+. And we can see a number of different indicators. So for example, here we see an indicator here going from a red color through orange to a yellow, depending on what pH we are at. We see here phenolphthalein going from colorless to a light pink to dark pink as we increase in pH. We can see here the structure showing what's actually happening, how we're changing these colors, and how the structure is changing as we add hydroxide or add protons to the system. So this direction adding hydroxide, this direction adding protons, and what's happening to the structure and how the structure change causes that color change. So for the example here, when the indicator, the protonated and non-protonated equivalencies are about 1, when they're about a 1-to-1 mole ratio, the color is a mix of the colors of the original color of the non-protonated and the protonated versions of the indicator. When the non-protonated and protonated versions of the indicator, the mole ratio here difference is greater than 10, the color will be from the non-protonated form. When pH is greater than pKa, the color of the non-protonated form dominates. Because if pH is greater than pKa, this is my equivalence point, this is my half equivalence point. When pH is greater than this, I have more of my non-protonated form than my protonated form. So here, the concentration of my non-protonated form is greater than the concentration of my protonated form. When the ratio of the non-protonated to protonated, again, A minus to HA, is less than 0.1, the color will be in the form from the indicator. So when I have a large portion of the protonated indicator, when I have a large portion of the HA form, the color will be dependent upon the color of the HA form. When pH is less than pKa, the color of the protonated form dominates. So the protonated indicator concentration is greater than the non-protonated indicator concentration. Most titrations, the titration curves show a very large change in pH for very small additions of base near the equivalence point. You will see this in lab. The indicator can be used to determine the endpoint of the titration if it changes color within the same range as the rapid change in pH. What do I mean by that? I mean equivalence point versus endpoint. Your equivalence point is where the number of moles of acid equal the number of moles of base. Whether it be weak acid, strong acid, I don't care. The number of moles of acid equal the number of moles of base. Stoichiometrically perfectly equal. The endpoint is just past the equivalence point. At the endpoint, there's an excess of your titrant. So whatever you're adding. From the burette. For adding base, like the picture shown here, that means I have excess base. This is where the indicator reacts with the excess. And if it's in the right range, can change color. So phenolphthalein is often used in acid-base titrations because it's going to turn to a light pink color around a pH of 8, 8.5, depending on where you're at. So phenolphthalein is one that if you've ever used the titration where it's gone from colorless to pink, you've used phenolphthalein. But there's a lot of other ones as well. Again, the pKa of the indicator is approximately the pH at the equivalence point. Here's a list of indicators from your textbook that you can see that we can actually use. Some have multiple ranges, so like thymol blue is good for the about 2 to 4, 3.5 range, but also good again between the 8 and 9 range. The one I mentioned was phenolphthalein. Phenolphthalein goes from colorless to pink as I reach a pH between 8 and 9. Other ones in here that are really common, crystal violet thymol blue is pretty common. You'll see other ones depending on which experiments you're doing. Bromothymol blue, bromocrystal green, methyl red, bromothymol blue, phenyl red. You may use other ones in lab. But you should be able to pick on this chart, depending on where the pH value of the pH of your equivalence point is, you want to find one that's going to change color at that point. So if you need to pick an indicator, let's say you have something that's endpoint is around pH 7. Well, you see this, if it's starting out acidic below 5, all of a sudden we're at 7, this might be a good one, okay? If you can go up higher, you can go up to pH, if this is going to change, if your whole equivalence point is going to be going like this, and you're going from 5 to 9, anything in that range, like phenolphthalein would be really good for that. Nitrophenol, maybe not so good because it's ending about 8.5. And it's really going just kind of colorless to yellow. Whatever is going to make the most sense to your eye to see and works within that range is a good indicator.